Hi. Today we're going to talk about limits involving infinity and also negative infinity. Just to let you know where we're at, this is the last video on limits, so that finishes up the chapter. And the whole course, Calculus 1, only takes 6 chapters. So we are making some progress here. There's two things that could be approaching infinity: the function value themselves or the independent variables. Let's talk about the first case initially. In fact, we've already talked about this somewhat. In other words, this should look like a familiar function. It's a rational function that has a polynomial divided by a polynomial. We know that polynomials are continuous everywhere, so we know that function is going to be continuous everywhere except at values of x where the denominator equals 0. And the only value that is at x equals 2. So what's happening at x equals 2? Well, if we take the limit as x approaches 2, the numerator is approaching 2 times 2 or 4. The denominator is approaching 0. So you have a number divided by something really, really, really small. It's going to make things either go to infinity or negative infinity. And we've talked about, at that point, we have an asymptote. And we should say that it's a vertical asymptote because it's straight up and down. And we can even name it. We could name it as x equals 2. And we could even draw it in here. And if you were asked, what's the limit as x approaches 2 for this function, we could just say does not exist, because infinity isn't really a number, it's a concept. But if we really want to get more information about what's happening on that function, it might be a good idea to go a little step further and look to see what's happening as x approaches 2 from the right and from the left. So if we take the limit as x approaches 2 from the right, we see that the numerator is getting really close to 2 times 2 or 4. The denominator is getting really close to 0. But it's not really 0. It's something close to 0. Well, I've kind of made up my little own way of talking about what is a small number close to 0, but it's not really 0. Because sometimes this is positive and sometimes it's negative. So I'm going to put a little plus in front of this. Mind you, this is my own terminology, but it helps me understand what's going on here. Now we see the numerator is getting really close to 4. The denominator is getting really close to a real small positive number. That's what this means. Because why? Because when you approach 2 from the right, x minus 2 is always going to be positive. So what do you get when you take a positive divided by a positive? You get a positive number. So this is going to approach infinity. We know what's happening to this function as x approaches 2 from the right. It's going up to infinity. And if we took the limit as x approaches 2 from the left, if you use a similar type notation, the numerator is still going to be getting really close to 4. The denominator is going to get really small. But what's a number to the left of 2? Like 1.99. When you subtract 1.99 minus 2, you're going to get a negative number. So I'm going to make a little symbol here that indicates that's a really small negative number. And a positive divided by a negative would be a negative infinity. So that means as you're approaching 2 from the left-hand side, we're going down to negative infinity. And we know more about the function than just knowing that it's a vertical asymptote. We know exactly what the function is doing around x equals 2. It would help us graph that function if we were trying to do that. Now, besides does not exist, it would really, you have three choices: infinity, negative infinity, or does not exist. Well, since one side's going to infinity and the other side's going to negative infinity, this is really the best way to describe the limit, because it really doesn't go to the same place. Now, we spent quite a bit of time on that, but we've really answered 4 different questions they could ask you on a test. They could ask you for this limit, they could ask you for this limit, they could ask you for this limit, or they could ask you, what is the vertical asymptote? And you would just write x equals 2. Remember, an asymptote is an equation, so don't put 2 as your asymptote. Put x equals 2. Okay, let's look at another example. Again, we have a constant, which you could even consider a simple polynomial divided by a polynomial. This is going to be continuous everywhere except at 0. So what's happening at x equals 0? Well, if we take the limit, since we have a number divided by something small, we know we have an asymptote. It's a little harder to do because it's right on the axis, but the y-axis, or x equals 0, is going to be our vertical asymptote. So we've answered one of the questions they could ask us. What is the limit as x approaches 0 from the right? Well, you get 1, that doesn't change, over a really small number squared. That's going to make it a positive small number. So we can see a positive divided by a positive is positive. And similarly, if we approach 0 from the left, we still have a 1 in the numerator. Now these are negative values of x, but we're squaring them. Since we're squaring them, it's still going to be a positive small number. So we're still going to infinity. Well, since both sides go to infinity, we could say the limit as x approaches 0 of that function really is infinity. Now, saying does not exist is not wrong, but it doesn't tell us as much about what's going on that function at x equals 0. We now know that it's doing what? It's going up like this. And by the way, if this was negative 1 over x squared, the only difference is these would all be negative infinity. So we could see what the function negative 1 over x squared, at 0 anyway, would be going down like that. So we've got different possibilities when we have a vertical asymptote. It could go like this, up to infinity. It could go like this, down to negative infinity, or it could go this way or this way. So we formed like a dance. It's an asymptote dance. Up to infinity, down to negative infinity, or it does not exist. So those are the possibilities with an asymptote. Okay, how about if we take one more example like this? The function 1 over the cosine of x. Get a trigonometric function involved. So we see the numerator is continuous everywhere, but the cosine of x, what does the cosine of x look like? That starts at 1, goes like this. So we're going to have a bunch of values at x equals pi over 2, and x equals 3 pi over 2, and x equals negative pi over 2, all those values, the cosine is going to be equal to 0. Therefore, we have vertical asymptotes at all those places because we're going to have a number divided by something getting really small. So we're going to have a vertical asymptote at x equals pi over 2, at x equals 3 pi over 2. We're going to have all these vertical asymptotes. I'll just write one of them. X equals negative 3 pi over 2. Okay, what about the limits? Well, if we take the limit as x approaches pi over 2, let's say from the right. Now, this is going to be a little bit tricky. 1 is just 1, but we have to have knowledge of the cosine of x over here. Here's pi over 2, and what happens is you approach pi over 2 from the right. Look at it. As you approach it from the right, all these values are getting close to 0, but they're all negative. So what you're going to get is you're going to approach a small negative number, so it's going to go to negative infinity. If we take the limit as x approaches pi over 2 from the left, we get 1 over, now as you approach pi over 2 from the left, we see all those values of the cosine are positive. So we get infinity. And I won't write it down, but what would be the limit as x approaches pi over 2 of this function? It would be does not exist. One side's going to infinity, the other side is going to negative infinity. Now, is it going to help us graph this function? Well, I think it is. Because what do we know? If we just take a couple values we know, the cosine of 0 is 1. The cosine of pi is negative 1. And the cosine of negative pi is negative 1. We can just see as x approaches pi over 2 from the right, it goes to negative infinity. So here's pi over 2. It's going to go down to negative infinity. From the right, we know, from the left, it goes to infinity. So if I'm approaching pi over 2 from the left, from this side, I'm going up to infinity. And you have an idea what it has at pi over 2. Now, if you tried at 3 pi over 2, you'd see it goes down to negative infinity, and you'd get something that looks like this. It takes a bit to do, but we're graphing and finding out something about a really quite complicated function. And some of you have probably already kind of guessed, what if we just graphed? The reciprocal of the cosine function is the secant function. So this is a good way of finding out what the secant function looks like. So that involves when limits of functions where the function value itself is going to infinity or negative infinity. Now, the other thing that we have to look at is, what about the independent variable? What if we have some functions as x is approaching infinity, or also negative infinity? What happens to the function? Well, a lot of this can be done just by common sense and knowledge of what functions are doing. Like, for instance, x squared. What happens as x gets really large? What's 1,000 squared? It's a huge number. 1,000,000 squared. It's getting astronomically large. So we kind of just know without doing any calculation that that approaches infinity. That limit would just be infinity. Well, what about as you're approaching negative infinity? Well, if you took a negative 1,000,000 and squared it, you're going to get a huge number, and it's still going to be positive, because a negative times a negative is a positive. So this answer would also be infinity. And you kind of know that that's what happens. As you approach, as x gets really, really large or really, really small, the function values get large towards infinity. What if you were taking x cubed? What's a large positive number cubed? It's even larger. This one is going to go up to infinity. But what happens if you take a negative number? What as x approaches negative infinity? Now, a negative number cubed is going to be negative, so it's going to go down to negative infinity. It's going to go down like that. And we kind of know that that's what the function x cubed looks like. A little more complicated one. What about the 10th root of x as x approaches infinity? Well, you might say the 10th root, that's going to make things really small. But remember, x is approaching infinity. So if you put 10 billion in here, one with 10 zeros, you're only going to get 10. So you see, at first you're thinking it's not going to grow that large. But remember, you can make x as big as you want. So even this function, it's not going to approach infinity like this. It's going to approach it very, very, very slowly. But it's still, the answer is still going to be infinite. Okay, just a couple more. What about the sine of x? Well, what's our knowledge of the sine of x? The sine of x just keeps going back and forth between +1 and -1, +1 and -1. Does it ever really go to one particular value? No, it doesn't. So this one, all we can say about it is it does not exist. It just keeps wandering between +1 and -1. Now, if you get the sine of x divided by x, start to think about what's happening. The sine is going to be a number smaller than or equal to 1, and the denominator, as x approaches infinity, is going to get huge. So your fraction is going to start to look like a small number divided by a huge number. That fraction is going to get really close to 0. Like, what if you took the sine of 1,000,000 divided by 1,000,000? Your fraction would be less than 1 over 1,000,000. And as x gets bigger, it even gets smaller. So this function is actually going to go and approach 0. Now, some of you might be remembering that we did something with the sine of x over x, but that wasn't as x approaches infinity, that was as x approaches 0. So here's x equals 0, and we found out the limit as x approaches 0 was 1. So we had this undefined function value at 0, but it was approaching 1. Well, what's going to happen is, this is just going to keep going like the sine of x, but it's going to keep getting smaller function values until eventually you're not going to see any difference. I don't have quite enough room here, but eventually this sine function is going to look, you're not even going to see the wavering of it anymore. It's going to look like a straight line. So again, the answer is going to be 0. Okay, so let's finish up this chapter by looking at some fairly complicated functions. So we're going to deal with rational functions because they're some of the most interesting ones as far as limits are concerned, especially involving infinity or negative infinity. So, first of all, what can I look at this complicated function and say, what's happening as x approaches infinity? Well, the numerator is going to get really large, and the denominator is going to get really large. So you're going to get basically infinity over infinity. Well, just like when the numerator and the denominator are both approaching 0, this is called an indeterminate form. We don't really know what the answer is going to be. It could be infinity, it could be 5, it could be 0. There's a lot of different possibilities. It's indeterminate. It really depends on how fast these functions are going to infinity. Just like in this case, it depended on how fast the functions were going to 0. So, those of you who have taken a pre-calc course probably learned a method for doing this. And it involved dividing everything by the highest power of x in the denominator. So that would be x cubed. So if we divided this by x cubed, we would get 2 over x squared minus 7 over x cubed. This would be 1 plus 9 over x squared. And then as x approaches infinity, when you have a number divided by something huge, everything is going to 0. This is going to 0, this is going to 0, and this is going to 0. So you get 0 divided by 1, or just 0. And that would be the answer to that. And there's nothing wrong with doing that. But I'm going to show you a little something here that might make this whole thing easier. And it comes down to this problem. What would you rather have? X cubed dollars or 10,000 x squared dollars? Well, I think it really depends on what x is. I think if x is equal to 1, I would certainly pick 10,000 x squared over 1 cubed or $1. But we're talking about x approaching infinity. Would you rather have 10,000 times infinity squared or infinity cubed? Well, especially if you think of infinity cubed as infinity times infinity squared, this is going to be 10,000 of those infinity squareds. This is going to be infinity of those infinity squareds. So this number here, as x approaches infinity, is so much larger than this that I would just throw that on the ground and not even miss it if I had this much money. If you can buy that argument that x cubed is bigger than any number you could put on here, x squared, we can do something called forming an end behavior model for this function. It's not the exact same function, but as x approaches infinity or negative infinity, it basically does so close to the same thing that we can call it that in the limit. So what would this be in the numerator if I ignored everything but the highest power of x? I could just wipe out the 7 and call that 2x. In the denominator, x cubed is so much bigger than 9x as x approaches infinity, I could throw out the 9x, and I'm left with that, which I can reduce to 2 over x squared. And since I claim they're going to have the same limit as x approaches infinity or negative infinity, what are you going to get? 2 over a huge number, it's going to go to 0. I didn't have to go through all that division. And if you really are thinking here, you're going to say, maybe I can make this job even easier. If I really can ignore everything but the highest power of x in the numerator and the denominator, if I have a case where the highest power of x here is less than the highest power of x here, I don't have to do anything. I know the answer is always going to turn out to be 0 because that higher power of x in the denominator is going to overtake what it is here. So if I saw this problem on a test, I wouldn't do this and I wouldn't do this. I would just say, oh, the answer is 0. And I would be very confident that I'm right. Okay, let's try a second one. This one is another rational function. I could go through this process. I'm not going to bother doing that. Instead, I'm going to form the end behavior model for this function. I'm going to ignore the 9, and I'm going to ignore the 3x squared minus 12x. What's left? 3x cubed and x cubed. And when I divide those, I just get 3. So I'm left with the limit as x approaches infinity of 3. Well, that doesn't even involve x, so the answer is just going to be 3. That was really easy. And I think if you're thinking ahead a little bit, you're going to say, hey, what happened here? We had the highest power of x in the numerator was the same as the highest power of x in the denominator. The answer is just going to be the coefficients divided. So if this happened to be a 2x cubed, the answer would just be 3/2. So again, if you had this on a test, you wouldn't have to go through any analysis. You could just look at the coefficients of the numerator and the denominator because the highest powers of x were the same. So, what else do we have now? We have something new about the function that we've learned. We learned that as x approaches infinity, the function is going to approach 0. It's going to be right along the x-axis, which means it's going to go like this. It's going to approach 0. So we can call y equals 0 what we're a horizontal asymptote. This function right here has a horizontal asymptote, y equals 0, because that's basically what this function becomes as x gets really large. And I think you can see it doesn't really matter if x was approaching negative infinity, this would still go to 0. So I'm not trying to graph this perfectly, but I know that y equals 0 is going to be a horizontal asymptote at both ends of the graph. We're learning something about this function. And the same thing is going on here, except instead of 0, the function is approaching 3/2. So right here at y equals 3/2, there's also going to be a horizontal asymptote. So somehow the function is going to approach that asymptote at both ends of the graph. So we've learned some new things. We've learned a new type of asymptote, horizontal asymptote, to go along with our vertical asymptotes. Okay, well, let's try the third case. In this case, we have a higher power of x in the numerator than in the denominator. So what we have to do is do an end behavior model. Remember, it's not the same function, but I can give you a function that's very close to this as x gets really large or really small. So I'm going to ignore the 20x squared, I'm going to ignore the 1, and rewrite this as x to the 4th over minus 100 x cubed. And if we're going to be smart about it, let's now divide both the numerator and the denominator by x cubed. And we get that. So what happens now as x approaches negative infinity? The numerator is going to be a really large negative number. The bottom is only negative 100. A negative divided by a negative would be a positive, but it's going to infinity. So it would just be a positive infinity. And I don't think I'm going to go into it right now too much, but the function begins to look like negative 1/100th x, which is just y equals negative 1/100th x is just a straight line. So we kind of know as x approaches negative infinity, it's going to go to, let's see, let me look at this. We have, so it's going to go to positive infinity. Let me make sure we did this right now. So we have a negative infinity divided by a negative infinity is, or by a negative 100 is infinity. Now, in this case, where x is approaching infinity, again we have a higher power of x in the numerator than we do in the denominator. So I can do the n behavior model, and I can ignore all this lower power stuff, and what do I have? 2x to the 5th over 4x cubed, which is basically just x squared over 2. That's our n behavior model, 1/2 x squared. We actually have a parabolic asymptote. And you can see whether x is approaching infinity or negative infinity, this is going to go to infinity. So somehow it's going to go up like this, or it's going to go up like that. Now, I can see, I was a little confused, and you probably saw that. This answer turned out to be infinity. That's a positive slope. The slope of this graph is going to be negative 100th x. So it's going to go like this. So the function, as x approaches negative infinity, it's going to go up to infinity. So we know it's going to keep going in that direction, and it's going to be boundless in that direction. So sorry about that. By drawing in that, this line would be y equals positive 1/100th x. This negative one shows the asymptote that function would take as it's going in that direction. So anyway, that pretty much finishes up limits. The more practice you do, the better you're going to get. But what this really does is it leads us to the next topic. We're going to have a new operation on functions that we're going to learn next that's going to give us all kinds of fun applications that we can do. So be prepared for derivatives of functions. Thank you.